In this episode, we will be exploring the process of how nuclear fuel is produced, from mining to enrichment. Let's dive in.
Before me dropping value bombs of this video, I would like to introduce the Nuclear Power Engineering Principles course, now available on Udemy. This comprehensive course is your ticket to mastering the principles of nuclear power engineering and taking your career to new heights. Packed with engaging lectures, this course is designed to provide you with a deep understanding of nuclear power engineering principles. And the best part, upon completing the course, you will receive a prestigious certificate of completion to showcase your newly acquired skills and knowledge. It is a valuable credential that can open doors to exciting career opportunities in the nuclear power industry. Don't miss out on this incredible opportunity to unlock your potential with Nuclear Power Engineering Principles course. Enroll now and gain access to this top-rated course at an unbeatable price. But hurry, as this offer won't last long. Join us today and take the first step towards a successful career in nuclear power engineering. Enroll now in the Nuclear Power Engineering Principles course on Udemy and unlock your potential. Don't wait and start your learning journey now. Now, if you're interested, the link to this course is provided in the video description below.
The production of nuclear fuel involves several key steps, starting with the mining of uranium, which is the primary fuel used in most nuclear reactors. Uranium is a naturally occurring element that is found in small amounts in the Earth's crust. It is extracted through open pit or underground mining, depending on the location and quality of the uranium deposit. Mining is the first step in the process of producing nuclear fuel. Uranium, which is the primary fuel used in most nuclear reactors, is a naturally occurring element that is found in small amounts in the Earth's crust. Uranium mining involves extracting uranium ore from the Earth's surface or underground deposits. There are two main methods of uranium mining: open pit mining and underground mining. The method used depends on the location and quality of the uranium deposit, as well as economic and environmental considerations. The first method is open pit mining. In open pit mining, also known as strip mining, a large excavation, or pit, is made in the ground to extract uranium ore. This method is typically used when uranium deposits are close to the surface and are of relatively low grade. Overburden, which refers to the layers of rock, soil, and other materials covering the uranium deposit, is removed first to expose the ore. The uranium ore is then extracted and transported to a processing facility for further treatment. The second method is underground mining. Underground mining is used when uranium deposits are deeper in the ground and of higher grade. This method involves excavating tunnels and shafts to access the uranium deposit, and the ore is extracted using various mining techniques, such as underground drilling and blasting, as well as ore haulage and ventilation systems. Underground mining requires specialized equipment and techniques to ensure the safety of miners and the surrounding environment. Once the uranium ore is extracted, it is transported to a processing facility for further treatment, which may include crushing, grinding, and chemical treatment to separate the uranium from other minerals and impurities. The processing of uranium ore, also known as milling or beneficiation, is an important step in the production of nuclear fuel, as it prepares the ore for further processing and eventual use as fuel in nuclear reactors. It's worth noting that uranium mining is strictly regulated by national and international bodies to ensure safety, environmental protection, and public health. Regulations and best practices are in place to minimize the impact of mining activities on the environment, including measures to prevent water contamination, air pollution, and soil degradation. Additionally, radiation protection measures are in place to protect miners and ensure safe handling and transport of uranium ore. After uranium ore is extracted through mining, it is typically transported to a milling or beneficiation facility for further processing. The goal of milling or beneficiation is to extract the uranium from the ore and convert it into a form that can be further processed to produce nuclear fuel. The milling or beneficiation process involves several steps. The first step is crushing and grinding. The uranium ore is typically crushed and ground into fine particles using crushers and ball mills. This process helps to increase the surface area of the ore, making it easier to extract the uranium. The second step is leaching. The crushed and ground ore is then treated with a chemical solution, typically an acid, to extract the uranium from the ore. This process, known as leaching, involves dissolving the uranium from the ore into a liquid solution. The third step is separation and purification. Once the uranium is leached into the solution, it is separated from other minerals and impurities. Various chemical and physical processes, such as solvent extraction, ion exchange, and precipitation, are used to separate and purify the uranium from the leach solution. The fourth step is conversion. The purified uranium is typically in the form of uranium oxide, also known as yellowcake. Yellowcake is a solid powder that is further processed to convert it into a form that can be used as fuel in nuclear reactors. This may involve converting yellowcake into uranium hexafluoride, UF6, which is a stable compound that can be transported and stored more easily. And finally, the fifth step is packaging and transport. Once the uranium has been processed into a form suitable for further use, it is typically packaged in specialized containers and transported to fuel fabrication facilities, where it can be converted into fuel rods for use in nuclear reactors. It's important to note that the milling or beneficiation process is tightly regulated to ensure safety and environmental protection. Strict regulations and best practices are in place to manage and dispose of radioactive waste generated during the milling process, and to prevent water and air pollution. Additionally, radiation protection measures are followed to ensure the safety of workers and the public during all stages of the milling or beneficiation process. After the milling process, the uranium is typically in the form of uranium oxide, also known as yellowcake. Yellowcake, also known as uranium oxide, is a solid powder that is an intermediate product in the production of nuclear fuel. It is produced through the milling or beneficiation process of uranium ore, as mentioned earlier. Yellowcake is typically in the form of a fine, yellow-colored powder and is the most common form in which uranium is transported and stored. It is an important intermediate step in the conversion of uranium ore into fuel for nuclear reactors. Yellowcake is primarily composed of uranium oxide, U3O8, which is a compound made up of 3 uranium atoms and 8 oxygen atoms. The exact composition of yellowcake can vary depending on the specific ore source and the processing methods used. Yellowcake is a stable compound that is relatively insoluble in water, which makes it suitable for storage and transport. It is typically a fine powder with a yellow or beige color, although the exact appearance can vary depending on the specific ore source and processing methods. Yellowcake is usually converted into other forms before it can be used as fuel in nuclear reactors. One common conversion method is to convert yellowcake into uranium hexafluoride, UF6, which is a stable compound that can be easily transported and processed. This conversion involves reacting yellowcake with hydrogen fluoride, HF, to produce UF6, which is a solid at room temperature but can be easily converted back into a gas for transport. Yellowcake is a radioactive material and must be handled and stored with strict safety precautions. Workers involved in the production, handling, and transportation of yellowcake must follow radiation protection measures to ensure their safety and prevent exposure to radiation. Similarly, strict regulations and best practices are in place for the transportation, storage, and disposal of yellowcake to ensure environmental protection and prevent any potential risks. The production, handling, and transportation of yellowcake are regulated by national and international authorities, including the International Atomic Energy Agency, IAEA, and national regulatory bodies. These regulations aim to ensure the safe and secure handling of uranium and its products, including yellowcake, throughout the entire nuclear fuel cycle. Overall, yellowcake is a critical intermediate product in the process of producing nuclear fuel. It is a stable and transportable form of uranium that undergoes further processing to convert it into a form suitable for use in nuclear reactors. Strict regulations and safety measures are in place to ensure the safe handling, transport, and storage of yellowcake, and to prevent any potential risks to human health and the environment. This material is then shipped to a conversion facility, where it is converted into uranium hexafluoride, UF6, a stable compound that is used as the feedstock for enrichment. Enrichment is the process of increasing the concentration of the fissile isotope, uranium-235, U-235, in uranium hexafluoride. Most nuclear reactors use enriched uranium as fuel because it allows for a sustained chain reaction, which is necessary for the production of energy. There are several methods of uranium enrichment, including gas diffusion, gas centrifugation, and laser enrichment. In gas diffusion, uranium hexafluoride is passed through a series of porous barriers, and the lighter U-235 isotope diffuses more rapidly than the heavier U-238 isotope, resulting in a slight increase in the concentration of U-235. Gas centrifugation involves spinning cylinders of uranium hexafluoride at high speeds, and the heavier U-238 isotope is forced towards the outer edge, while the lighter U-235 isotope collects towards the center, resulting in an enrichment of U-235. Laser enrichment uses lasers to selectively ionize U-235, which is then separated from U-238 using electric or magnetic fields. Once the uranium hexafluoride is enriched to the desired level, it is converted back into uranium oxide and then converted into uranium pellets, which are small cylindrical pellets that are loaded into fuel rods. These fuel rods are then assembled into fuel bundles, which are loaded into nuclear reactors to generate heat through a controlled chain reaction, producing electricity. It's important to note that the production of nuclear fuel, from mining to enrichment, is strictly regulated by national and international bodies to ensure safety, security, and non-proliferation. Stringent safeguards, inspection, and monitoring measures are in place to prevent the misuse of nuclear materials and technologies for weapons purposes. That's it for today's episode on how nuclear fuel is produced, from mining to enrichment. We hope you gained a better understanding of this complex process. If you're enjoying learning about the exciting world of engineering on our channel, be sure to hit that like button and subscribe to our channel. It really helps us out, and you won't want to miss any of our upcoming videos.